Centered at the origin and in the xy plane is a ring of radius 5 meters with a line charge density of 5 nanocoulombs per meter. You are asked to find the potential at the origin. So you're really being asked to find the potential difference between the origin and infinity. Let's draw a figure. Right at the origin, the electric field intensity will be 0. A common error is the conclusion then that the potential at the origin is 0. The potential at the origin is the amount of work it takes to move 1 coulomb of charge from infinity to the origin. And it will take work to do that because you have all this positive charge along this ring. When phi changes by the amount d phi, you'll sweep out a distance on the ring of charge of 5 meters times d phi. There will be a charge associated with this dl, and it will be the line charge density rho sub l times dl. So that dq will equal 25 nanocoulombs d phi. We can find the potential at the origin due to this dq, just like we did in the previous problem, by taking our charge and divided by 4 pi epsilon sub 0 times the distance where we want to find the potential from where our charge dq is, which is 5 meters. To find that potential due to the charges all along the ring, we just integrate from 0 to 2 pi. All these terms are constants, so the integral from 0 to 2 pi of d phi is just 2 pi. So 5 goes into 25, gives us a 5. 2 pi over 4 pi will be a 2. Let's substitute in for epsilon sub 0, and nanocoulombs is 10 to the minus 9. And these meters cancel. The 10 to the minus 9s cancel. 2 over 36 gives us an 18. We will have a 5 times 18 pi, and a farad is a coulomb per volt, so a coulomb over a farad is a volt. So the potential at the origin is 90 pi volts.